Hey guys, it's Mr. Lyle. Last time we talked about gases and how they differ from the liquid and solid phase. That when we're in the gas phase, molecules are typically very far apart, but in the liquid and solid phase, they're closer together. And we talked about the fact that you're likely to achieve a liquid or a solid phase at lower temperatures because lower temperatures slow down molecules and gives them more of a chance to stick together. But the question becomes why, not why, but how do they stick together when they get close together? What makes them attract to one another? And in today's video, we're going to introduce the idea of intermolecular forces, these forces between molecules that allow the molecules to stick together. And that's key. You've got to have forces between molecules in order to attractive forces between molecules in order for you to form liquids or to form solids. So there are three major types of intermolecular forces, which I'll sometimes refer to as IMFs. And I'm just going to briefly introduce them right now, but know that we'll come back and study each one in depth. In fact, today, the focus that we're going to have is on something called a London dispersion force. And these are really, really weak forces that you see in molecules, all molecules. It doesn't matter if they're polar or nonpolar, but they're by far the weakest of the intermolecular forces. And we'll describe it in detail in just a couple of minutes. And next up are what are called dipole-dipole forces. That word dipole just refers to a polar molecule. So when we describe a dipole-dipole force, it's a force of attraction between two polar molecules. So of course, you're only going to see this in molecules that are polar, and that's it. And then a special subset of dipole-dipole interaction is what's called a hydrogen bond. Now, it's not a real chemical bond, but it's a force of attraction that appears in certain types of molecules that contain hydrogen and a few other elements. And we'll talk again in a few videos about that. So, like I said just a moment ago, today we're going to focus on just London dispersion forces, which sometimes we'll refer to as LDFs. And I'm going to give you the simplest take I can on a London dispersion force right now by looking at a simple helium atom, actually two of them. So in green on the left, I have two helium atoms. And the one that is on the right here, so this one right here, is what helium's typically going to look like. And what we're trying to display in that picture is that the electrons in helium are evenly distributed throughout the atom. And so there's no distortion to the atom at all. But it turns out that electrons are funny and they can, on their own, appear on one side of the atom or molecule for no apparent reason. We would call that random chance. And the picture on the left, this one right here, is an atom of helium that's, for whatever reason, its electrons showed up on the left side of the atom. How do I know that? Well, helium has two electrons total, and it looks as if this atom has been distorted. And you'll notice there's that partial negative charge symbol over on the left side of the atom. It's like we're saying that the two electrons, for no apparent reason, showed up on that side of the atom. And when we did that for a very brief moment in time, we have an atom which is normally nonpolar. It is temporarily polar because the electron showed up on one side of the atom. And that's what's referred to as an instantaneous dipole. It just means just for that instant, that atom has become polar. Now, if you proceed to the right-hand side, what you'll see is if that instantaneous dipole comes in contact with a normal nonpolar helium atom, it's going to cause that second atom to become polar on its own. Why is that? Well, what we would see is, again, if we have two electrons over on this side of the helium atom, the other side of the atom is positive in charge. What's that positive charge going to do? It's going to attract electrons from the other atom towards that positive charge. Okay. And so at that moment, we've produced another atom of helium that is polar just for that moment. And we call it something else. We call it an induced dipole. Induced means it was made to become that way. Okay. Well, what's the London dispersion force then? Well, you know that opposites attract. And now we have two molecules that are lined up such that positive is attracted to negative. So we would say that this kind of electrostatic charge, or I should say electrostatic attraction between those molecules right there, that represents a London dispersion force. It's a really simple idea. Positive and negative attract to one another. Now, the thing that we need to know about it is because it's temporary, it's also going to be pretty weak. Okay. It doesn't last for very long, but this is what's going to allow molecules to stick together. And that's what you have to have if you're going to have a liquid or a solid phase, at least with molecules. So if we got to a more complicated molecule like the fluorine molecule we were talking about before, that fluorine molecule has 18 total electrons. And we could think of it kind of in the same light. If for no apparent reason, for no reason at all 18 electrons showed up on one side of this molecule, then that molecule would become temporarily polar. This is what we would refer to, just like we did up here, as an instantaneous dipole. And just for that moment, this side of the molecule has become negative, and this side of the molecule is going to become positive. Okay. Now, when that molecule comes in contact with another fluorine molecule, the same thing happens again. The electrons are pulled over towards the positive charge on that first molecule. I'm not going to be careful to count all 18 electrons, but you get what I'm saying. All of the electrons shift over to this side of the molecule. This side becomes negative, and this side becomes positive. And again, sorry about that, we have what's referred to as an induced dipole. And induced, again, just means that that molecule was made to become polar just for that moment. And the weak attraction right there between those two molecules, that's what we refer to as the London dispersion force. It's how the molecules stick together, even if it's only temporarily. And that's how you get a liquid. Now, moving forward, what we're going to see is it matters how many electrons are present. So in other words, up here where we saw an LDF between two, I just erased it, where we saw the LDF between two helium atoms, that's a pretty weak attraction because there's only two electrons. So as I move down to fluorine, I see that that attraction is going to be stronger. Why? Because there's 18 total electrons in each molecule. Gives it a stronger attraction, and so they stick together better. It's easier to get them to stick together. So as we move forward, the question is going to be, what kind of properties can we judge based on kind of this strength of attraction between molecules with London dispersion forces? And that's for our next video. See you then.